It's really fun for me to come here and talk to such a lively and interesting group. I assume I'm going on the assumption that most of you are experimental students or postdocs, right? So this presentation is really built with that in mind. I guess another question, before we get started is how many of you have used materials project? Ooh, a couple. Okay, good. So you can, you may, if you're not, maybe this won't be so interesting in some ways, but you can keep me, check up on me and make sure I'm not saying anything wrong as well, or compare with your experience. Okay, so to get, for some reason, I don't know why this is not lining up, but let's see. Oh, it does work. Okay. So the first thing I want to talk about is, what first principles can do for you as experimentalists. And I would say that, basically every really good project in materials and quantum materials is going to have some first principles component to it. So I've taken from our speakers of this morning just a kind of a little sample. This is a paper by Judy. I don't know if she talked about it or not. I'm sorry I missed the talk. But in the paper, there is a first principles calculation and comparison with experiment for electric field tuning of the band gap in black phosphorus. Another example from Judy is, I should have cleared this with you first, is tungsten ditelluride thin films. And here, there's no first principles calculations in the paper itself, but the context of the work included predictions from first principles of some of the properties of the system, which would presumably help to kind of motivate and guide the work. So, the tungsten ditelluride has a predicted vial state. That's a first principles band structure calculation. The lattice thermal conductivity is also predicted in this paper that I've shown down here. Not to make Vigil feel left out, there's this, anytime you work with topological systems, basically there's always going to be some band structure calculation in there, either a model, either a full first principles calculation or something involving a model that ultimately goes back to a first principle, some kind of first principles fitting. And so that's no different here. In this paper, she's studying epitaxial thin films of tin telluride, and this theoretical, citing this theoretical paper to show how these interesting states are controlled by strain. Okay, so basically, if the time you're going to be coming to first principles is, there are two possibilities. You've already know what material you're studying, but you want to know everything you can know about it. Whatever's known, or you have an idea for doing some kind of measurement or experiment, but you're looking for the right material to study. You have some criteria for the kind of material you want, but you don't know exactly which material it should be, and you want to go out and look in the world of materials and find the right one for you. I think I should ask the same question about the crystal, so to look for in crystallographic databases, right? How many people have a login for ICSD? Okay, more, right? So again, that's a fantastic resource where you can get, you can just go in and without basically doing any work, you can just get information about the structure, about for a given composition, what are the reported structures, for certain structure types, are there any compounds with that composition? So you can, using this database, you can answer this question immediately. these, following in the footsteps of this kind of crystallographic database based on experimental information, we're building up first principles databases where the information in the database is not necessarily from experiment, but from a first principles calculation, which I'll argue a little bit later. You should think of as a kind of computer experiment. So, the data is data, right? And so this is a database. And the main ones are Materials Project, AFlowLib. There are others. It's kind of a competing ecosystem in which we're going to be evolving these databases. So, and I have no connection with Materials Project. So I'm not a member of the team. I'm not promoting Materials Project over other databases, but I'm just going to use it for the example here. And so if you have your computer open and you want to log in, if you want to open up Materials Project and log in, this is not a hands-on. We're not actually going to be doing hands-on tutorial. This is not. The mechanics of using Materials Project are very, very simple. You do not need me to teach you how to click here and click there. But if you're logged in, if you're on the wireless and you want to log in, there'll be a chance to do something in a minute. All right, so like right now. So if you go to Materials Project, the first screen that you see after you log in with your Google ID or something like that. You do have to log in, but you can just log in with your Google account. Are you logged in? Hey, you were nodding. Yeah, you were nodding. Did oh, anybody log in just now?
I'm trying.
You're trying. Okay. Report when you succeed.
The page is not working.
Did I spell Materials Project wrong or something?
The page itself is.
Okay, this is going to be, so a good thing I did the screenshots, because this always happens when you give a talk if you try to do it live. So the first thing, the first thing you see on the entering screen is a periodic table, and the simplest functionality that is offered is that you can put in some elements and see what compounds are formed in that, of those elements. And so if we do that, I've chosen a bunch of different things. Here, I was interested in, samarium boron 6. So I put in samarium and boron, and I get a list, and this is all the binary compounds that Materials Project has with samarium and boron. And there's a bunch of different entries. So already you see that, you're getting a lot of, this is a little bit like ICSD, right? If you did the corresponding search in ICSD, you're in. Okay, you can put in your favorite compound. We have a bunch of different structures, formation energy above the hull. So do people know what the convex hull is? Okay, so if you're at zero temperature, you're looking to find the ground state is the state with the lowest energy. So if the hull is the curve as a function of composition, which corresponds to the lowest energy compound or mixture of compounds of other stoichiometries that gives the defined stoichiometry at that point. So here we have, if you're zero, it's the ground state. If it's not zero, it's a higher energy state. But of course, higher energy states are also potentially of interest. They might be induced by, because we're just talking about energy here, not free energy or enthalpy. So these might be phases that are observed at higher temperatures. They might be observed under pressure. So they're not the ground state. They don't have the lowest energy, but they still could be observed. And Materials Project also includes some hypothetical structures as well. So I'll try to, if we can discuss that. And then there are some other information, the density, the volume, and so on. Another thing you get is the band structure, and again, you get the spaghetti. This is, I think I'm still in samarium boron 6, and a density of states. You can get, they produce calculated X-ray diffraction patterns for you. You don't have to do yes, you can do this yourself, but it's so much quicker. You can just, it's nicer when you don't have to. There are many, there's so many functionalities that are being added. There's a list of substrates that you could grow this thing on that have good lattice matching, and so on. Let's see. Okay, so I'm just gonna keep going forward linearly here. That was a pretty short list. Here's a list from, let's see, I feel like I skipped a page here. Oh, here's the first page. So some of these lists are quite long and have many, many different compositions on them. So they're kind of overwhelming. Like one of my favorite compounds, Barium Titanate, which is one of the prototypical ferroelectrics. You put that in and you get there's lots of phases that form in this ternary system, barium titanium oxide. A bunch of them are barium titanate in different space groups. And you kind of have to sort that out, like what the heck is this, Some of them are recognizable, like barium titanate and R3M is the rhombohedral ground state, ferroelectric ground state of barium titanate. There's the 0. And they're, typically the default is to rank them by the energy above the complex hull. So the lowest energy phases are given first, and then as you go higher in energy, it goes up. So questions about this? People, we're looking, this all makes sense so far, right?
Insights?
That I believe has to do with the number of atoms in the unit cell. So I can check that by, at least that goes with, let's say, barium titanate in the rhombohedral phase has 5 atoms in the unit cell, right? And some of these unit cells are getting quite large. So that's sort of interesting. Recently, they've also added for many compounds computed phonon dispersion relations. So these are the phonons in the Brillouin zone. Gamma usually appears a couple of times if you're used to looking at phonon dispersions. So here you can see the acoustic modes, and then a bunch of optic modes. And this is still rhombohedral. I think this is still rhombohedral barium titanate. And lots of other, a whole what I'm trying to give you, trying to convey here is that you can go in, put your compound in, look at this phase, and you'll be just like bombarded with information. So for rhombohedral barium titanate, there's also computed values for the piezoelectric tensor. There's a dielectric tensor, and a bunch of other, there's like fields all over the place with possible information. And I should mention, of course, that for any given compound, you're not going to get all of the information. Some of them don't have phonon dispersions. Some of them don't have band structures for reasons I'm not, so you get a kind of selection of computed properties depending probably also on what the material is. Like for if it's metallic, you're not going to get a piezoelectric tensor.
Karin?
Yes.
So do you know, for instance, how many compounds out of ICSD that they've... All?
Well, I don't want to say absolutely all because there's some pretty crazy stuff in ICSD.
Yeah, right.
But I think...
Stoichiometric compounds.
I think, they've sort of, I think there was an effort to try to put in anything, remotely reasonable from ICSD into here. So there's a pretty good, pretty good. I think there are things in ICSD that only have lattice parameters and huge unit cells that just might not have made the cut for this, because you do need, as I'll discuss, you do need to have the crystal structure, or at least some idea of the crystal structure, in order to generate this information. Okay, so this is just a little glimpse into the materials project, and so again, this is here. This is the message and the plan for this talk. So I first want to, I'm going to try to offer a little bit more about this. I'm going to talk a little bit more about this, to try to convince you of the idea that first principles calculations really offer you, the experimentalist, useful information about the structure and properties of solids. It's a very different, it's actually complementary to what you're seeing in experiments in the ways that I'll try to explain. Again, as experimentalists, with the emergence of databases such as Materials Project, you have immediate access to a whole bunch of first principles data, which even as recently as a few years ago, you would have had to somehow calculate yourself, right? Which you probably wouldn't do. But I mean, if you can just open up a page and look at it, why wouldn't you do that? Why wouldn't you want to know everything there is to know about a system that you're studying, or that you're considering? You're trying to select. You're making a decision about whether you're going to choose this compound or that compound for your measurements. I hope I'm not, sort of mischaracterizing what experimentalists do here. So that's the good news. The reason that I actually appreciate the invitation to come and talk at this school is that there are some things that you need to know that that are not as sort of rosy and positive. That if you just log into the Materials Project website, they're not really going to emphasize that part of it. So to interpret, so even once you have these results, to really understand what they're telling you about the compound is definitely, you definitely will benefit from having some knowledge of first principles methods. And even the amount that I'm just going to tell you in the next half hour will make a huge difference to how you see the information in Materials Project. Okay, I'll just give you sort of a sense of some of the questions that you should be asking yourself. And so, so that leads to the last bullet, which is if you're actually going to make a decision based on something that you're seeing in Materials Project, like a real decision, to work on this compound or not work on this compound, or set your parameters of your spectrometer a certain way, or if you're planning to actually publish something, that involves information, that includes in the discussion or the argument information that you got from this first principles world, you should do the relevant calculations yourself, which you shouldn't do unless you really know how to do them. That's what the star is. That's the old message. Or with a theoretical collaborator. And I really sincerely believe this. I'm not just saying this in order to keep myself, in business. Which it might sound like, yeah.
Have you seen a lot of publications coming out that are just referencing Materials Project, or
I don't
rather than doing the calculations?
I haven't really seen that. I don't know how much of that is going on without that. And in some sense, we're still at an early stage where just getting people to use Materials Project is the thing. And a couple of years ago, I was at NIST, and they actually had I forgot what they called it. They had a competition where you were supposed to write and submit a paper without doing any calculations, but only using what was in the database. You know, like the best paper would win. I don't recommend that. And, and again, I'm going to show you a couple of examples just to make sure you see what.
Do you foresee that happening, increasing in the future? Where?
Yeah, I think that, you know, people will. I mean, I think there's a tendency to sort of, if you get this information, to accept it and say, oh yeah, that's in the database. It must be, it must be right.
I know that's dangerous, but at the same time, it's very powerful, right?
Yeah, but again, I would never publish anything without redoing the calculation. And I'll show you some examples of, you know, things that are a little scary, right?
I think people do that already.
Okay, so it's your, okay, not you though, right? But you know other people.
I work with A-flows.
Right.
But I think people do say that.
Right. At some point, at some level, the message that the people from the databases is giving is you should do this.
Right.
You know, but I'm telling you, I'm taking my chance here to tell you something I think a little bit more serious, which is, you know, this is. You know, this is sort of, you can use this as, you know, this is an amazing tool and it changes the way you do things. But if you really are serious about, you know, being right, you need to check it.
Wikipedia.
It's like, oh yeah, I was going to say that. Yeah, thank you for reminding me. It's like Wikipedia. It's like the Wikipedia of materials. Okay, you know, like it's probably right, like it's definitely mostly right, or, you know, you like if it's not right, it should be, or, you know, it's not, or maybe it doesn't matter. But, you know, you, like if you're in high school or something, you know, you're not allowed to reference Wikipedia. You have to get like a real thing. Okay, so that's the perfect analogy. Thanks for bringing that up. Yeah.
Real versus hypothetical structures, is there a way to tell on the website or database that it is like real or hypothetical? And can you insert like certain parameters for your hypothetical structure that you're trying to like, you know, get more information about?
Okay, so I'm actually not, there is, in each entry, there's a little bit of information about where the structure, you know, came from, like did it come from ICSD? So that can help guide you a little bit. I think that some of there might be a functionality, but I've never used it, where you can actually generate a calculation. I think in AFlow, I'm pretty sure they have that a little bit more featured, and not just so there is that as well.
You can put in a hypothetical structure and compound?
Yeah, well, you can do that. One of the things that I encountered when I was trying to connect to Judy and Lydia's work, and I've had this problem before, is that, you know, they go very much by the space group. You know, like most of the structure sort of specified by the space group. If you're looking for the structure of like black phosphorus in here, and I have it on, I think I have it in my browser, you know, there's no entry in the line that says black phosphorus, right? You have to know the space group. So in order to recognize that that entry is black phosphorus, or, you know, T prime.
Doesn't exist.
It does.
Sure.
Well, not barium titanate, but.
Oh no, so you're understanding.
Oh, did you're looking in there, right? You were looking for your.
Looking for.
Okay.
Students trying to see.
Yeah. So is that like all the polymorphs in there? Okay. So anyway, so this is kind of part one. I got to keep an eye on the time because I'm, you know, but these are all important. These are all important messages.
20 minutes.
Okay. Really? So it was 45 minutes that we're doing this, or?
Sure. 20 minutes or less.
Okay. I thought we were doing an hour, but it's okay. It's not an hour?
Oh, we started a little bit late.
Yeah. Like at 1:15. Wait. All right. Well, you can pull the plug anytime. Okay. So I'm going to go through this pretty quickly. You know, this again because you may have seen this level of discussion of first principles before. You know, we're really studying the solid as a physical system of interacting electrons and nuclei. it's quantum mechanics. This is the real theory. Here's Dirac. And there's a famous quote from Dirac, which is usually misinterpreted. He says, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, which was used to explain that solid state physics is not really fundamental or interesting for many years. But that goes on to present the challenge. The difficulty is that the exact application of these laws are too complicated. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed so that you can study these systems without too much computation. And of course, so the first principles methods are these approximate practical methods, and the concept of what too much computation is, of course, has changed enormously since Dirac's time. So both of those things are working in our favor. I have a long discussion. I have a discussion again, which is very much from solid state textbook, the full electron-electron Hamiltonian, the adiabatic approximation, where you have the nuclei moving in the effective potential of the electrons, where this potential is the ground state energy for the electrons and the potential of the fixed nuclei. So the electrons are basically following the nuclei around and staying in the ground state. And if you have this ground state energy for the electrons and the potential of the fixed nuclei, then you can compute all kinds of things about the solid. And those are some of the things, including most of the things that we saw in our little visit into materials project. So just to give the flavor, looking just at a diatomic molecule where I have two positions and 1 degree of freedom, which is the separation r. If I can compute this E naught as a function of r, then I can predict the equilibrium spacing for that molecule, and I can predict its vibrational frequency by looking at the curvature at the minimum. I can do this if I have this function for a crystal. Then the set of positions is really going to be the structural parameters. For a simple crystal, like a simple square lattice, there's one free parameter. If I have E naught as a function of that parameter, I can predict the lattice constant, and I can predict the elastic constant for this case. I can do. Of course, if I can compare the energy of a square lattice with the energy of a hexagonal lattice or different structures, and so I'll put them here, I'll do the computation again, minimize the energy again, and I can predict whether this, well, not so hypothetical anymore since we're looking now at a lot of monolayer crystals, whether this thing will prefer to be in the hexagonal or the square structure by looking and seeing which one has the lower energy. Okay, and so that's how, these are the way I can predict the ground state structure. I can predict structural parameters, and the game can be played for crystals with more than one atom in the unit cell, or three-dimensional crystals. It's just that they're more structural parameters. So I'm looking in a multi-dimensional space, but I'm still able to compute this energy. My black box is still giving me this energy for a given structure, and then I'm using that to make these predictions. Again, this is a slide I've been showing for a long time, but it's a good slide. For perovskite, for example, for perovskite oxides, which are some of my favorites, like barium titanate, you get very quantitative predictions for the lattice parameters by playing this, by using the black box and minimizing the energy. These are the lattice parameters. They're about 1 to 2% off. Even the internal positions of the atoms in this tetragonal structure of barium titanate are well reproduced, and strontium titanate is correctly given as cubic here. you can compute phonon dispersion relations because you basically, these are just phonon, phonon dispersions, the force constants are just derivatives of the total energy, or changes in the force with atomic displacement. So you can build up the whole force constant matrix, put in the mass factors to get the dynamical matrix, and plot the phonon dispersion, say, of gallium arsenide. This is a classic paper from 1991, and compare it with experiment, and you get like good results, right? This is first principles prediction compared with experiment. And this is, you can also predict things that you didn't know in advance, like the phonon dispersion of gallium arsenide. This is work that I did with a postdoc back in 2010, where we looked at the spin-phonon coupling in another perovskite, strontium manganite, by basically doing a first principles calculation where we compared the phonon frequencies in the anti-ferromagnetic state with the phonon frequencies in the ferromagnetic state, which was a hypothetical, the hypothetical structure. And you can see that these phonon frequencies are quite, shift quite a lot from one phase to another. So this guy's stable, and this little I means that phonon is unstable. Yeah.
Does correlation effects have any role to play at all?
Right. So this is all in the black box, in that black box of how you compute E naught.
So usually band structure is not, you can't compute that very well if you have a strongly correlated system. But are you saying that the lattice constants, however, can be predicted pretty well?
There are, yeah. So you can, the functional includes some correlation effects, and then there are fixes. There are sort of add-ons that allow you to include more. So structures and phonons actually are pretty good in general, even for things like YBCO. Okay. So and we we actually compared this with experiment and showed that in fact this large spin phonon coupling really exists. So these are some of the, so if you know how to compute that E0 as a function of R, then you can compute, you can get the total energy as a function. If you can get that, then there's the suite of first principles methods give you crystal structure and structural parameters, phonon dispersion, and elastic constants. And then the question is, what is in this black box? Again, we want to get back on schedule here. So you understand, if I can compute this, I can predict structure and phonons, right? But what is in this black box, and how much can I trust the black box for different kinds of materials? So again, there are two ingredients that go into the black box: density functional theory and pseudo potentials. Again, in a short time, I'm not going to explain the whole theory of this, but again, the idea of density functional theory was a really groundbreaking idea. It was that you could express the ground state energy of the interacting electron gas in a fixed potential, like the potential of nuclei, as a variational function of the electron density, just the electron density. And if you minimize, and then you'd vary the electron density, the electron density that minimizes the functional would be the ground state electron density, and the value of the functional is the total energy. So that's the story there. The catch is we don't have an exact form for the functional. But there are very good approximate forms. And again, I'm not going to go too much into the details, but one of the problems with early forms of this functional was that the kinetic energy, the quantum mechanical kinetic energy, was very poorly described. So you might have learned in a solid state course about the Thomas Fermi theory, or in a quantum mechanics course, which is actually a density functional theory where the kinetic energy is just described using the kinetic energy of the free electron gas. That's like a terrible approximation for most materials. And so the key here is that Kohn Walter Kohn and Lou Sham came up with another way to treat the kinetic energy. They basically replaced the true kinetic energy by the kinetic energy of a non-interacting gas with the same, in an external potential with the same ground state charge density. So a lot of the quantum mechanical aspects of the kinetic energy got captured by that. And so A, that works a lot better, and B, when you crank through the implications of that statement, that you're going to map it onto these equivalent, map the system onto a single particles moving in an effective potential, you get single particle, a self-consistent system of single particle equations that gives you what looks like a band structure. Okay, and so you crank through this, you get something that looks a little bit like again, it's self-consistent like Hartree-Fock, except it's not quite Hartree-Fock, but you get a band structure. And then to finish the construction of the functional, you then fit the remaining things to quantum Monte Carlo calculations of the interacting homogeneous electron gas. And that gives you kind of like the simplest functional that contains some correlations, some interactions. It contains a pretty decent description of the kinetic energy, and that's called the local density approximation, which is often abbreviated LDA. And that's a very old functional, goes back to the to the 60s, but people still do calculations with it because it actually captures a lot of systems pretty well. Of course, people have done many more functionals. They're not systematic, but it's not really systematically improvable. You build in extra physics for particular applications. Okay, so before I just want to point one thing out here. So if I do a calculation of the hydrogen atom, okay, I'm watching the clock too. One electron in the field of one fixed proton. That's like the only quantum mechanical problem we know how to solve. Right. Suppose I solve it with the framework that I just, so I should be able to solve this with my black box. If I put this potential and this electron into my black box, you'd think I would get minus 13.6 eV. But I don't. I get minus 8.1. Okay, and that's because the self-interaction cancellation is not exact. Okay, so this already, this is, I don't want to destroy your confidence in this process altogether. Like the self-interaction problem here is huge because there's only one electron, but it's just that's something I like to puzzle people with that when I'm teaching them density functional theory. So here are these, you have the one electron calculations. You get band structures that look pretty much like real band structures, except they're not quite right in general if you compare them with ARPEs or something. The band gaps are often off by like a factor of 2. The bandwidths are not, are also off by some percentage. But if you just look from far away, it looks great. Okay, it looks, and that's really because these single particle energies are not really the band structure. They never were meant to be interpreted that way. They were just a tool for handling the kinetic energy part in the density functional theory. And any resemblance, is more confusing. It's sort of semi-useful, but you have to be a little bit careful with that. And you can go beyond DFT to get better band structures. So let's see. Again, I'm feeling a little constrained by time. 10 minutes? Oh, okay. So I'm going to just calm down. Okay. The other ingredient that makes this all work is something called pseudo potentials. And the when people were first trying to solve the quantum mechanical problem and get energies that you could use for this kind of structural optimization, but if you were doing all electron calculations, it turned out that that just was never going to work because the core electrons have so much energy that the energy differences are way, way out in the significant figures, and you couldn't get meaningful results for looking at like those curves that I showed you. So the thing you have to do is you have to get the core electrons out of the picture, and for many solid state purposes, the core electrons don't really care about the solid state environment. They could as well be frozen, subtracted out for all time if you have a way to do that. And the way to do that and to just get an effective theory where you have valence electrons moving in the effective field of the core is pseudo potentials. And then you have much smaller energies because you just have valence electrons. And then you can compute these energy differences accurately. Okay, got the idea, right? If you didn't know it already. So you're basically writing an effective theory of valence electrons in an effective potential of the ions. And the valence electron inside the core is modified. It's replaced by a smooth function, which gives you much lower energies. And you can expand the function in plane waves. So this was absolutely brilliant insight, which basically got the whole field started. Cone sham by itself was not enough. You only see total energy calculations starting in the 80s with the introduction of these kinds of pseudo potentials. So here the wiggles are replaced. The wave functions match outside the core, but inside the core for small r in an atom, you have the wiggly thing replaced by a smooth nodeless function. There are good potentials and good and bad pseudopotentials. There's an infinite number of ways to construct this effective theory and modify what's going on in the core. And you have to be careful not to choose which pseudopotential you're using to get the right answer. Again, when you're doing a materials project, that's not such a critical problem. But that, let's see, where's my thing? Oh yeah. If you're computing properties that depend on the wave function at the nucleus, don't do it with pseudopotential calculations, because the wave function nucleus has changed. Right? So you're not going to get hyperfine splitting and Mossbauer effect. There are ways to do that, but not in pseudopotential calculations. Okay, so this gets me to, so here we're back here. These are I've talked a little bit about the fact that you get something that looks like a band structure, and you can in many cases you can get kind of useful information out of it, but you have to be a little bit careful. Anything that depends on the band structure is similarly it's more like a guideline. It's not super quantitative. And then we also can compute electric polarization and get polarization quantities out of that. That's actually pretty good. Some of the limitations of first principles calculations are we're typically doing periodic systems, so solid solutions are very difficult. So that's where I would go to Ichiro Takeuchi and say, please help me with your combinatorial spreads, because you can do it so much better than we can. Defects are very hard, and that's what I meant before when I said that first principles calculations in many ways are complementary to what you can do with experiments. So for me, it's easy to study like a perfectly ordered, perfectly stoichiometric system, and it's hard to study a system with defects and substitutions. Experimentalists, it's the opposite, right? Your systems are full of like defects and disorder. And sorry, And that limit of the perfect order is not that easily accessible, I try to sort of put a good spin on this from my point of view, saying that, with this perfectly ordered calculation, I can help you separate what's really intrinsic to the system to, things that are sample dependent or going to depend on disorder and defects. And I also, I'm coming back here with my point about the computer experiments. I really, believe, I really see first principles calculations as a kind of computer experiment where we're generating data about the electrons and the atoms at the atomic scale that can be, treated and used as information about the system, used as the basis for making phenomenological models. And another way in which we are so much better than experimental is that the synthesis step is like nothing. Okay, so if I want to make a perfectly ordered superlattice of compound X and compound Y, it takes me like 10 seconds, and it's going to take somebody doing MBE, like oxide MBE, like a year, if it if it even ever works at all. So on the other hand, this is good because we can compute some properties for you and say maybe you should spend a year making the superlattice, it's that interesting, or not, right? So again, so it's very complementary. Okay, so last section here, just to give you, so the whole development of materials project and these kinds of first principles databases are funded by this Materials Genome Initiative, which was started in 2011. Before you all were born or whatever, but so you think it's been around forever, but it hasn't. This led to a huge interest in high throughput calculations, where you would pick a large set of candidate systems and do first principles calculations and look for specific properties, like in the so-called band structure or in the crystal structure or in the phonon frequencies that had to do with the phenomena that you were interested in. And some of the papers that you can see, there are papers here that so some examples of papers are ones where people searched for new two-dimensional materials using data filtering and ab initio calculations. Did you know this paper? Or? Oh, okay. Well, I'll just keep going. Looking for topological insulators. Again, you have a bunch of candidate compounds. You crank out the band structure and look for that band inversion. Looking for Dirac materials. That's another topological feature in the band structure. And so this is that takes us here. That takes us here. Okay, wait a second. I think I changed my strategy again. Keep going. Oh yeah. So I want to kind of close out with. Remember, I was telling you, you need to be a little careful. You can't assume that just take everything for granted that is perfect. So let's look at gallium arsenide. Gallium arsenide, should be slam dunk, right? There's no everything. That's the simplest thing that you could possibly imagine. I mean, Marvin Cohen in 1966 did a great job on gallium arsenide. So let's look at gallium arsenide. Here's the materials project entries for gallium arsenide. There's the our zinc blende structure. So let's go to there and look at the band structure. What is this? This looks nothing like what you think of. I mean, to me, I look at this and that doesn't look anything like that, which is the band structure that you see in a textbook for gallium arsenide, right? I mean, and what's this zero gap doing here at gamma, right? That's really scary. I can make it look a little bit more like the band. I can make it look a little bit more like the textbook one by rescaling it. So this is now rescaled, and if I couldn't do too much about the fact that it's a different path through the Brillouin zone. But this looks marginally like this, except there's no spin-orbit coupling, right, which of course is important for gallium arsenide, if you're many properties, but it's not there in Materials Project. Not in gallium arsenide anyway. I mean, we could take a look together at something like with iridium in it. But this is what I'm, this is what I want you to be saying, right? Like, there's no. What do you mean there's no spin orbit coupling, right? How about the phonon dispersion, right? This is a beautiful paper from 1991. If you look at the phonon dispersion in Materials Project, that's what it looks like, which looks pretty crazy to me. And I tried the same rescaling, but even then, there's some pretty weird things going on here, like this. There's a bump here. I mean, this is not good. Okay, there's some, again, it's not quite the same path through the Brillouin zone. But if I start to look in detail, there are things that, especially in the upper bands, that I'm really not happy about. And I know that they don't match experiment because that one.
I thought phonons, I thought they should be able to get phonons pretty well.
Yeah, and look, and we did in 1991, right? What's going on here? This is high throughput.
Oh.
So, you've basically just you crunch through like 10,000 compounds with a kind of fixed set of calculational parameters, and you haven't looked too closely at any individual compound or about what you might want to know about an individual compound. And I'm not criticizing. I'm still like, this is an important step. We will get there, and this is like a step on the way to this awesome state of affairs where we can just get this information like in 10 seconds. But this is what I want to show you, that even for something that we understand as well as gallium arsenide, that
Well, I can understand that the electronic band structure may be way off, but do you understand what corners are they cutting that would result in this kind of difference?
I actually only was, I was only doing this for this. This is new. Like, you don't remember this from last year, right? So I was. This problem with the phonons is something that I'm working with a postdoc at Rutgers, and we're looking at phonons in 2D monolayers, and a lot of what's published is really just wrong, because they are not using, because the interpolation methods that they're using to go from a sampling of points to the full dispersion relations is bad.
Oh.
Okay. And I can show you like specific papers where they have these crazy wiggles that they just published, and I'm like, I look at that, like, I know that's not real, and it's not.
So is that one of the key problems with the high throughput? That it's just basically the computing?
Well, no, it's just that it's like one, we went from a kind of what I would call the artisanal, first principles calculation, where you spend like a year on each compound, like really getting into its soul, to trying to do 10,000 compounds, with a kind of fixed parameter set, and one size does not fit all. It's like a first cut. Like, if you don't look too close at that band structure, at that phonon dispersion, it's not too bad. But when you start to look at details, then you see problems.
Do you know what they are doing currently to go through a second cut?
I don't know. I mean, I gotta look into this. And again, I'm gonna, this is like getting taped, and someone's gonna come to my house, like, and break my knees, or like cut off my access to Materials Project.
Sorry, you're only talking about Materials Project.
database.
But anyway, so I hope that was kind of illuminating. And so I'm just going to wrap up here with, just to recount that, to basically say, yeah, actually, if you're interested in learning the methods, that's good. I'm not discouraging you from that, but that's less necessary than it was now that we have these databases. But this is the slide I showed you before, and I'm basically just bringing back this message, hoping now that I actually made these points, at least, to some extent. And I'm happy to take any quick questions.